Hey, this is Team Mamba Mentality, and today we're going to be presenting our Advanced Spacecraft Lighting Control System. I'm Team Leader Eduardo Cantu, and alongside me are members Omar Beg, Saeed Jafari, and Yash Patel. Our mission for this project was to update NASA's current spacecraft lighting network system. We wanted to do this by implementing features that increase power efficiency and allow crew members to access lighting fixtures through an easy to use interface. We also wanted to include features that help maintain circadian cycles for all crew members, and we did this by mimicking the sun rising and the sun setting. To go over what this project contains, it includes 4 different lighting sources and a web server that can control their lighting intensity and measure color spectrum, as well as a housing enclosure with the lighting and hardware included. The main features that we wanted to go for were maintaining circadian rhythm and monitoring light degradation status. We would like easy light source expandability, and this will be done via Bluetooth, as well as allowing notifications for any possible cutoff in connection. We're now going to be going into the design portion of our project. Initially, for our design, we were leaning towards FPGA development for our lighting protocol that we would use for the network. But from the figure that you can see from the right, it isn't meant to be understood without proper explanation, but it is meant to convey the complexity that came with that kind of system. So we decided to go instead with the Raspberry Pi and Arduino network to provide more concrete results and easier debugging for our COVID-related epidemic that we're in.
Hi, this is Yash. Here we have a typical deployment of a system on board a habitable module. There will be one Raspberry Pi installed, which will be the master control or the main controller on board a craft. The Raspberry Pi has a built-in Bluetooth capabilities and can connect to several different devices at the same time. Each space with a habitable module will have its own Arduino, to which several different lighting fixtures and light intensity and color sensors can be installed. The example here shows a typical deployment on board a habitable module that houses astronauts in this crew's living space and the crew rest space and a lab space. The lighting profile can be independently set in each one of the spaces as required. For example, the living and rest spaces will be specifically programmed to follow a pattern and intensity that imitates a day and a night as they were on Earth. On the other hand, the lighting in the lab space will be adaptive, where, for example, it will be profiled to promote plant growth. These profiles can be configured using the GUI, which will be available when the Raspberry Pi is installed using a monitor, mouse, and a keyboard.
A typical system with a one-space installation consists of one Raspberry Pi, one Arduino, one Bluetooth module for the Arduino, and one or more light intensity and color sensors, light fixtures, and DMX shield. The Raspberry Pi is what the graphical user interface runs on, and it can be controlled using the monitor, mouse, and keyboard connected to it. It is capable of communicating to several different Arduino microcontrollers wirelessly using Bluetooth. The Raspberry Pi requests light sensor data from Arduino microcontrollers periodically to ensure both health and accuracy of the send commands being implemented. The Arduino microcontrollers control elements within a space. The light intensity and color sensors connected to it, and the Arduino collects data from it and passes it upstream to the Raspberry Pi when requested. It also controls the LED light fixtures connected to it within a space. It communicates with the Raspberry Pi wirelessly using Bluetooth and communicates to the sensors and light fixtures on a wired connection, specifically using a DMX shield for the light fixtures. The color spectrum sensor or the light sensor is connected to the Arduino and can read RGB color values. It can measure light intensity of up to 500 lux. The Bluetooth sensor has a Bluetooth 4.0 capability that sets up a communications bridge between the Arduino microcontrollers and the Raspberry Pi within a range up to 100 meters. The Raspberry Pi can connect to up to 8 different Bluetooth modules, which translates to the fact that there can be 8 different spaces controlled with one Raspberry Pi. The DMX shield is an attachment to the Arduino microcontroller, and it establishes a communications link between the microcontroller and the LED light fixtures.
So here's a visual of the Arduino setup. Going from left to right, you can see the first thing we have is a Bluetooth module, which is connected onto the breadboard. Below that, we have the DMX shield, which is responsible for the connection between the Arduino and the DMX light. And below this DMX shield is actually the physical Arduino. And then on the top right, we have our color spectrum sensor, which is responsible for sensing our light intensity and colors.
The graphical user interface is able to accept sunrise and sunset times from the circadian rhythm, measure the light intensity of the light sources, as well as monitoring the degradation of the light sources. When the user opens the GUI, they will be able to input the RF COM ports for each light as well as the circadian rhythm. When the sunrise and sunset times are set, the lights will gradually light up or dim by 25% every 15 minutes. This will continue until the light sources are all at DMX input value of 255 for lighting up or 0 for dimming down. As well as circadian rhythm, the GUI will be able to monitor the light degradation of the light sources by showing a notification on screen at less than 50 lux when not supposed to. In addition, the system is able to notify the user that the Arduino is disconnected from the Raspberry Pi through Bluetooth.
There were a few shortcomings due to the COVID-19 pandemic that's currently going on. One of them being that all of our meetings were virtual, and so not all of our primary goals were able to be accomplished. One of them being the fact that we wanted to create an enclosure for the system. At first, we thought we could accomplish this. After finding out that one of our team members actually contracted the virus, we decided it'd be best to not meet at all in a physical setting, and thus everything was put onto a virtual setting. So it was difficult to construct this enclosure because of that. Not only that, some of the secondary goals were also set back because of this, including constructing the voice command system and the plant growth system. After completing our project, we decided to do some further research to see what other implementations and ideas we can add to this lighting system. After doing some research on published patents, we saw some interesting patents that kind of pushed our own ideas into ways to expand the lighting system. This included creating a self-adjusting lighting system based on the viewing location, as in where a viewer would look at a certain area, whether it be a screen or a room, and the light would automatically adjust to the needed brightness of the person. In addition, one of the patents that we came upon was a lighting alertness system, which also could be very well used within a spacecraft for the purpose of keeping alertness within the astronauts and crew members.